Welcome to the online narrated lectures for CM2101. This week we will finish our discussion of vibrational spectroscopy by looking at polyatomic systems. In Part 8 we will begin by discussing the normal modes of polyatomic systems. When we were studying diatomic molecules last week, we realized of course that there is only one vibration, there is only one bond. There cannot possibly be more than one vibration. With polyatomic molecules, we can certainly have more than one mode of vibration. We refer to these modes of vibration as normal modes. But I will define exactly what we mean by normal modes later. Because diatomic molecules have only one mode of vibration, there was only a single fundamental band. With polyatomic molecules, we can imagine that we can have a fundamental band associated with each normal mode of vibration, assuming that all the normal modes are non-degenerate and infrared active. Let's have a look at two triatomic molecules and see how many fundamental bands are visible. First, let's have a look at water, H2O. In this spectrum, you can see three peaks, one at a relatively low frequency of 1595 wave numbers and two at high frequencies at 3652 and 3756 wave numbers. Next then, let's look at carbon dioxide. In this spectrum, you can see two peaks due to CO2 at 667 and 2349 wave numbers. The peaks around 3700 wave numbers are due to water. So despite these two molecules having the same number of atoms and the same number of bonds, they exhibit different numbers of peaks. We will see that what determines the number of peaks is not just the number of possible vibrations in the molecule, but also whether the vibrations are degenerate and whether the vibrations are intrinsically infrared active. Let's first discuss what determines how many vibrations a molecule can have. Both H2O and CO2 have three atoms. But do they have the same number of vibrations? How many different ways can they vibrate? Let's look at a triatomic molecule. We describe the position of an atom in the molecule with three coordinates. This means that in order to describe the motion of each atom, we also require three coordinates. We can say that each atom has 3 degrees of freedom. If we had but a single atom in the system, then each of these 3 degrees of freedom would be purely translational in nature. If we had a diatomic molecule, then we would need 6 coordinates to describe the motion of both atoms, and thus there would be 6 degrees of freedom. The motion of 3 atoms in a triatomic would require 9 coordinates, and there would be 9 degrees of freedom. In a polyatomic molecule of n atoms, therefore, there are 3 times n degrees of freedom. When we have more than one atom, these degrees of freedom can be written as combinations of atomic coordinates that describe translations, vibrations, or rotations. First, let's look at translational motion. To describe the position of a molecule, we can specify its center of mass with 3 coordinates. We can then describe the translation of a molecule from one position to another by identifying the change in the 3 coordinates of its center of mass. Therefore, every molecule has 3 translational degrees of freedom. A pure translation is one in which, during the motion, there is no relative change in the internal coordinates of the molecule, that is, no rotation and no vibration. So of the 3n degrees of freedom for a polyatomic molecule of n atoms, 3 of those degrees of freedom can be identified as pure translations. To describe a rotation of a linear molecule, we require 2 angular coordinates. These angles can be the azimuth, phi, and colatitude, theta, in spherical coordinates, as depicted in this figure. In the same way as when we discuss linear molecules, we discuss rotation in terms of two component rotational axes. Therefore, for linear molecules we have two rotational degrees of freedom. This enables us to determine the number of vibrations. The number of vibrations is simply the number of degrees of freedom, which is 3n, minus the number of translational and rotational degrees of freedom. This will be 3n minus 3 for the translations and minus 2 for the rotations. Overall, therefore, a linear molecule has 3n minus 5 vibrations. In a nonlinear molecule, we require three angular coordinates to describe rotation. We have the azimuth and colatitudes as before, but we also need another angle to describe the molecule's internal rotation. Therefore, for nonlinear molecules, we have three rotational degrees of freedom. This means that for a nonlinear system, the number of vibrations is once again simply the number of degrees of freedom, which is 3n, minus the number of translational and rotational degrees of freedom. This will be 3n minus 3 for the translations and minus 3 for the rotations. Overall, therefore, a nonlinear molecule has 3n minus 6 vibrations. This means that nonlinear systems have one fewer vibrations than linear systems with the same number of atoms. So let's return to our two triatomics, water and carbon dioxide. Water is nonlinear, and so we expect it to have 3n minus 6 vibrations. As n is equal to 3, this means that water has 3 vibrational degrees of freedom. The infrared spectrum has 3 bands, so it would appear that all the bands are infrared active and non-degenerate. For carbon dioxide, we have a linear molecule, and so we expect 3n minus 5 vibrations. This means that carbon dioxide has 4 vibrational degrees of freedom. However, the infrared spectrum of carbon dioxide shows only 2 bands. We will explain this shortly. Before we continue, we need to formally define what we mean by normal modes of vibration. Any arbitrary set of displacements of atoms can be expressed as a superposition of 3n minus 6 in the case of a nonlinear molecule and 3n minus 5 in the case of a linear molecule, normal modes of vibration. A normal mode of vibration is one in which all the atoms move in phase with the same frequency. The centre of mass remains fixed so that there is no co-translational motion. The vibrational energy is quantized. The motion is described approximately as simple harmonic. Each normal mode is independent and to a good degree of approximation is not affected by other normal modes. And finally, if the molecule starts vibrating in a normal mode, it will continue to do so. It will not transform into another normal mode. Let's see if we can understand this in terms of carbon dioxide. Vibrations involve stretching of bonds. Let's consider the CO bonds in carbon dioxide vibrating separately. We have a left bond vibration and a right bond vibration. However, these vibrations are not independent. If we excite the left vibration, then because this involves motion of the central carbon atom, the right bond will be affected and the right vibration will be excited. The normal modes of vibration associated with stretching are in fact a linear combination of the left and right vibrations. If we add the left and right vibrations together in phase, then we get the symmetric stretch nu1, and if we add the left and right vibrations together out of phase, then we get the asymmetric stretch nu3. This time, exciting the symmetric stretch does not lead to the excitation of the asymmetric stretch. On the right of this slide, we have the 4 vibrational normal modes. You will notice the symmetric and asymmetric stretches that we saw on the previous slide, but there are also 2 bending modes which have exactly the same frequency. These bending modes are thus degenerate. You can see that the bending modes are related by symmetry. You can transform one mode into the other by rotating about the internuclear axis, which is of course a symmetry element for this molecule. The fact that the bending modes are degenerate explains why one band is missing from the infrared spectrum. If you excite fundamental transitions of either bending mode, it occurs at exactly the same energy, and so the spectral lines will lie on top of each other. In this animation, you can see the symmetric stretch, the asymmetric stretch, the bending motion, and the superposition of all modes. Let's see that again. Notice that the bending modes have been added together in a way that makes them look like a kind of rotation around the axis. I will try to illustrate this more clearly in class on Thursday. The superposition is simply the addition of all modes. The motion appears to be chaotic, but this is what we would see at the molecular level. It is important that although we discuss the vibrational modes separately, that you appreciate that the motion of the atoms is described by a linear combination of all the vibrational modes. Each normal mode has its own set of vibrational energy levels, each with their own set of vibrational quantum numbers. There are 4 vibrational quantum numbers, V1, V2A, V2B, and V3. And if all of these quantum states are 0, we can identify the 0-point energies associated with each of these modes, as given here. Note that the total 0-point energy of the molecule will be the sum of the individual 0-point energies. It is the total 0-point energy that the molecule will have at 0 Kelvin. That is, when V1, V2A, V2B and V3 are all equal to 0. In this case, the total 0-point energy will be equal to a half nu1 plus nu2 plus a half nu3. This is the end of part 8 of topic 5. Please continue on to part 9.